So hi everyone, my name is Xueying. I'm a graduate student from the Millet class. And today I would like to talk about the global methane emission. That we interpret the global methane emission from 2 years of satellite measurement from TROPOMI. And our focus is on the sensitivity to OH, the methane sink, and to the sensitivity of methane sources. And in the beginning, I want to thank my co-authors and their contributions.
One second. They're having a little trouble hearing you. So I think you'll need to just speak loudly. And
Okay. So methane is a very important greenhouse gas. The concentration of methane in the atmosphere has been accelerating increase in the past decade. And showing here is the global methane budget in the past decade from the Global Carbon Project. And those two values listed are one from bottom-up estimate.
I'm just going to share here. Good.
Okay, thank you. So back to the presentation, here is the global methane budget in the past decade. And those two values are from two kinds of estimate. The first one is from bottom-up estimate. It's more like how much methane is emitted per animal, then times with animal population, to based on the bottom-up statistics. Well, for the second estimate, it's from the top-down estimate. It is a methane emission quantified by observations. We can see there are very large discrepancy between those two estimates, more than 150 teragram per year. And here is the global methane sink. If we manage the global emission with a global methane sink, we will get the change in the atmosphere methane abundances. In the bottom-up view, it is more than 100 teragram per year methane would remain in the atmosphere. However, observation indicated this value is actually about 10 to 20 teragram. So my job here is to explain what are the causes for the discrepancy between the bottom-up estimate and the top-down estimate. To do that, we use satellite measurement from TROPOMI. This illustrates how TROPOMI observing the Earth. It gives us an unprecedented opportunity to quantify the methane emission variabilities. Provide around 7 by 7 kilometer square pixels of near daily overland global coverage at 13 local time. The methane retrieval is based on combining information from short-wave infrared and near-infrared. Shown here is TROPOMI 2 years methane observation oversampled to 0.1 degree. This data set is very fantastic because it can provide very detailed spatial distribution of the methane concentration enhancement. We can see just as here over California near Mississippi River, and all those clear spatial patterns in the Middle East that might reflect fossil fuel activities, and also in Northern India, South Asia, in Amazon Basin, and Central Africa. So here I'm going to interpret those 2 years data for an improved knowledge of the global methane budget. To do that, for the 2 years of TROPOMI data, we use the first 2 months to optimize initial condition, and then run the inversion from January 2018 to February 2020. But we only analyze the solution from May 2018 to October 2019, so that we would get the first 4 months to reduce any bias remaining in the model initial condition, and get the last 4 months so that the solution would be constrained by at least 5 months of observations. We optimize the monthly grade level methane emissions at 2 by 2.5 degree. Also optimize the 2 years mean hemispheric OH. And our inversion have 4 strategies. Those strategies are more like a sensitivity test, varying the assumption of prior emission. And we also have 3 OH treatment. This OH treatment is very important, as you will see later. For the first one, we use a fixed OH that using the prior OH estimate as a fixed constraint. For the second and the third, we optimize both OH, the methane sink, and the grade level methane source simultaneously in the inversion with different prior uncertainty estimate. The inversion result is evaluated against the independent data set from OPSPEC. And OPSPEC is an in-field data collection, also on a global scale. Our inversion is done at 2 by 2.5 grade. However, we further downscaled the emission into 0.1 degree based on the 2 years global methane observation over samples and the prior emission uncertainty. So the downscaling is relying on 2 assumptions. The first one is higher methane concentration reflect higher emission. The second one is larger prior emission uncertainty will indicate a larger emission correction prompted by the inversion. This spatial downscaling is evaluated by LC, and it has comparable performance at a 25 kilometer inversion. The reason that we did not do the inversion at 0.1 degree is because of computation cost. And this is our solution about the inverse analysis. Shown here as the prior methane simulations, and in the bottom is the TROPOMI observation. And on the right is the optimized methane simulation from fixed OH and optimized OH cases. You can see the fixed OH and optimized OH give us comparable reduction of the model methane column bells reduction. Those 2 inversions also provide a comparable reduction for bells in the independent data in OPSPEC, mainly reflecting the mean bells. However, even though about those agreements that we have seen previous, the inversion imply incompatible methane budget. As shown here, X is the global methane emissions, while Y is the global methane loss. And each symbol indicates the inversion result and also sensitivity cases. The size of those symbols is the best reduction of independent data set in OPSPEC. We can see that the fixed OH converge at a lower global methane flux, while all those optimized OH converge at another side. So furthermore, I'm going to interpret which solution is better. To do that, we use other atmosphere measurement about OH and CO from ATOM aircraft measurement across Pacific Ocean. And shown here is the latitude variance of OH on the left, also the data density. Comparing with the observation, shown here is the black line, the optimized OH solution is lower than observation. This indicated that the optimized OH is underestimate the model atmosphere observation. This also reflects as the CO measurement. The major sink of CO is also OH. So we can say the optimized OH overestimate the CO observation. This also indicated an underestimate of the OH. Therefore, the solution shown here indicated that optimizing methane source and sink simultaneously, simply based on the methane observation, is level post, even using the dense TROPOMI data coverage. If we compare with the fixed OH solution and the observations, we can see they actually match. They actually have a good fit in terms of OH and CO measurements. This indicated that the prior OH already have a good representation of the model. So next, I'm going to focus on the fixed OH solution. And this is optimized global methane sources. And shown here in the right on the top is the optimized emission. And those dots indicated where the solution do not vary agree across the sensitivity cases. You can see for the large sources regions, they actually agree. So this gave us confidence about our solution. And in the bottom is the emission question compared to the bottom-up inventories. With the emission overestimate in the northern hemisphere high latitude regions and underestimated in tropical and subtropical regions. Those are the solution from the 2x2.5 grid. Next, I'm going to present the drivers of those emission correction after we perform the spatial downscaling into a 0.1 degree. And this downscaling enables us to look into the emission hotspot. And shown here in the left is the emission increase in the past decade from the Edgar, the bottom-up estimate. You can see the Middle East is a very crucial region with intensive emission hotspot increases. Well, shown here in the right is a hotspot correction from the fixed OH. The color here indicated whether those hotspots are overestimated or underestimated in prompted by the inversion. You see that the Middle East is a key region and it may be related with the rapid increase of fossil fuel activities. And those emission increase are consistent across the season. Well, another key region we see is in the South Asia, where the emission correction has a seasonal pattern. If we zoom in into the South Asia, this is the emission correction period each month. And the amount labeled in the title is the total emission correction compared with the bottom-up inventory across this entire region. So the emission increase mainly occurred during July to October. In July, it starts in the northeast of India following the monsoon onset. The monsoon onset data is labeled in the bottom here. Then the emission increase extend to the entire North India and is diminished and shift eastward in October, following the monsoon withdrawal. And across the entire monsoon season, there are around 10 to 30 teragram methane emission increase over the South Asia. And one potential reason we are trying to relate the emission increase with emission process is related with monsoon rainfall. Because the monsoon rainfall would increase the water extent, then increase the emission from wetland, waste, and also maybe from animal manure management. Okay, so to sum up, we combined 2 years of TROPOMI methane data in just-in adjunct model to optimize for the global methane budget. And we found even using the satellite very dense data coverage, optimizing methane source and sinks simultaneously is low cost. The best solution yield at around 588 teragram per year global emissions. And the two important regions, one is in the Middle East, with rapid increasing about fossil fuel activities. The second one is in South Asia that potentially related with monsoon rainfall. And with that, I would like to thank the community for the opportunity to present our research, and we'll be happy to take any questions. Thank you.
I noticed in your results, for just the global results for both the fixed OH and the optimized OH, it looks like one area where the model still doesn't do a great job is over South America.
Yeah.
So do you think is that just like misrepresentation of sources, or I don't know, have you had any thoughts or looked into that at all?
Yeah, I think it might relate with data coverage because TROPOMI has a relatively lower data coverage over that region due to cloud.
The cloud coverage.
Yeah.
Maybe there's just a lower constraint.
Yeah, maybe.
Okay. Thanks.
What's the
cloud cover do you have to throw out data? You want less than 10% cloud cover? Or is there?
No, if there is a cloud, the retrieval will not be successful.
Yeah.
So there is, there is a data gap.
I got a question for you. This is Satish Gupta again.
Hi.
You mentioned that it's a monsoon that's causing or linked to methane emission. Did you find that same relationship or some kind of relationship with the areas where they grow rice, because they have a lot of wetlands? And you showed mostly in India. You think, how about the countries like Indonesia, Philippines? They grow quite a bit of rice.
This is a good question. For the region of Indonesia, Philippines, it's more like an island, so data coverage is also an issue. So the inversion is under constrained, does not give us a very robust solution. That's why we focused our solution into the North India. But it would be great if we can have in-field measurement over those wetland-rich island regions.
Thank you.
Okay.